We're now going to take a look at a new form of cycle, quite a bit different from the heat engines we've been looking at thus far, either the gas or the vapor cycles. We're now going to move into the area of refrigeration and refrigeration cycles. And what we'll do is we'll ask the question, if we were to take a heat engine and put work into the heat engine, would we be able to transfer heat? And it turns out the answer to that question is yes, and that is the basic premise by which a refrigeration cycle works. But it's essentially one whereby we put work in, and our working fluid going through, by rejecting and absorbing heat, we can actually transfer heat, and that becomes the idea or the premise behind the refrigeration cycle. So that's what we're going to take a look at in the next few lectures. So the question that we're asking here is, if we put work into a heat engine, will we actually be able to reverse the direction of heat flow? And so that is what we're going to take a look at. But in order to start that, what I'm going to do is I am going to ask a question. And that question is, what happens if you expand a compressed gas? Because that is kind of fundamental to the whole idea of refrigeration cycles. And so what we're going to do, we're going to take a look at a quick video of the process of compressing a gas and then expanding it, and we'll take a look and see what happens. So let's watch that now. So what we have is a standard compressor. We have it compressing now. On the right-hand side, you can see the pressures within the tank and the regulator, and on the left-hand side, you get a view of the compressor itself. As we flip around, you're going to see that, first of all, there's the muffler, there's the crankcase, and the piston cylinder device. There's a copper tube coming out with fins on it. That is the compressed air coming out of the compressor, which is then flowing into a tank. The reason we have those fins is because compressed air gets hot, or compressed gas. And we're rejecting the heat by placing those fins on the copper tube running to the tanks. There are two tanks that are connected together, and we can see on the right now we're at 100 psi. The regulator peaks at 90 psi because that's what it's set at. The pressure continues to go up to 120, and eventually we get to 130 psi and the compressor shuts off. We let it sit for a while so it cools a bit, and then what we do is we open the tank valve. We do a rapid decompression, and you see, first of all, there's water. That's condensation from the air, and then there's a little bit of white stuff there, and what that white stuff is, that's actually ice formation. So when you rapidly expand the compressed air, it cools, and you even get to the point where you get ice formation. So that is the essence or the fundamental component within any kind of refrigeration cycle. We compress a gas, we cool it, we expand it, and after we expand it, it gets cool, we absorb heat, and then we would compress it again. So in a real compression cycle, it wouldn't have ended like we saw there. We would have had it in a continuous or closed cycle. And so that would be viewed as being a gas compression cycle. There are others that we'll look at, which are vapor compression cycles, where the fluid is going through a phase change. So that's what we're going to look at in the next few lectures. So these are the ideas behind refrigerators. Refrigerators are devices. We all know what a refrigerator is because we all have them in our homes for keeping our food cool. However, we can extend that even further to applications such as air conditioning for a house. It's the exact same cycle between a refrigerator or an air conditioner, and then there are industrial cooling applications that we'll talk about in a later lecture. So we have refrigeration, but we can also transfer heat in the form of a heat pump. Now with a heat pump, what we're doing is we're trying to provide heat to a location instead of cooling a location. So in the case of a refrigerator, we're cooling. In the case of a heat pump, we are heating, but they use pretty much the exact same cycle. Now, there are two main forms of refrigeration cycles that exist. So we have vapor compression cycles whereby the working fluid goes through a phase change, and we have gas compression. Now the one that I showed you with the Makita compressor, that was essentially a gas compression cycle. Had we not exhausted the air into the atmosphere, but actually had sent it through some coils, we could have achieved some cooling through the process. So those are the two different types. Now, when we're talking refrigeration, you'll hear about the units of refrigeration. Quite often we'll be looking at mass flow rates and heat transfer in kilojoules per second or kilowatts. But there is also a commonly used unit of refrigeration, and it is referred to as being a ton. So a ton of refrigeration corresponds to freezing 907 kilograms of water at 0 degrees C into ice at 0 degrees C per day. So it's going through the phase change process, and that is what we refer to as being a ton. If you're buying an air conditioner for a house, for example, quite often they'll say it's 2 or 3 tons, and that's what they're referring to with that specification. That potentially could be used a little bit more in North America than perhaps Asia. I've looked at air conditioning systems in Asia, and they usually just have kilowatts as being the units of refrigeration there. But nonetheless, ton is quite common, and it's used quite extensively. We also have refrigerants. And what a refrigerant refers to is the fluid that works within the refrigeration cycle that we're considering. So a refrigerant is the working fluid within our cycle, and it is what is absorbing thermal energy and then transferring it to another location as it goes through that process. And there are many different types of common refrigerants in existence. So what we do, we have the chemical formula for whatever particular refrigerant we might be looking at, and I'll write that out. So that is the first one. This is called R12, and commonly it had a trade name called Freon. Now we don't use this anymore because what was happening is it was going up into the upper atmosphere and was destroying the ozone layer. So that was R12. NH3 is ammonia, and it is labeled as being R717. That is used more for commercial applications. Air, like we saw in the opening video clip, that is R729. And another one, C3H8. This is actually propane. Got to be somewhat careful with that because it's explosive. But it as well has its own refrigerant number. So the one that we'll look at mainly in this course, we'll look at both gas, so we'll look at air, and we'll also look at another refrigerant, R134A, and that's a common replacement to Freon, R12, because it's more ozone friendly. So that's what we're going to be looking at, refrigeration cycles, in the next few lectures.